Hello, welcome to Notes on Dalton's Law. We will do this twice. First we'll introduce Dalton's Law, and then we'll use Dalton's Law again once we get through all the gas laws. So Dalton's Law says that the total pressure inside of a container is equal to pressure 1 plus pressure 2 plus pressure 3 and so on. This second formula right here is just another very specific type of Dalton's Law. Notice it's still total equals one pressure plus another pressure. There's just two here. And this is when we collect a gas over water. So P total equals P H2O plus P gas. And this would be your dry gas. So you have water vapor, and your dry gas. These standard pressures are on page 2 of your packet, so the back side of the cover page. And they also should be at the top of your Dalton's Law 1 worksheet. Any of these can be set equal to the other to convert, but these are considered standard pressures. So for example number 1, let's begin. It says the container holds 4 gases. It's just so you can focus on the question with me. Carbon monoxide, oxygen, nitrogen, hydrogen. The partial pressure of the 4 gases are 1.8 atmospheres, 6.5 atmospheres, 3.6 atmospheres, and 8.9 atmospheres, respectively. What is the total pressure inside the container? Okay, so partial pressure means part of the whole. Partial means part of the whole. So partial pressure of carbon monoxide would be 1.8 respectively, oxygen is 6.5, nitrogen is 3.6, and hydrogen is 8.9. So you're going to use that generic formula. You must present your generic formula in every example. This is what I mean by generic formula. So we know from Dalton's Law that total pressure is equal to all the parts inside the container. We know we have these 4 partials, or these 4 parts. So we're going to list that there, and we're going to add them up. And so now I'm going to plug in their numbers respectively to each piece and make sure their units are the same units of pressure. If their units were not the same unit of pressure, we would need to convert one to the other before adding. So make sure they're the same units of pressure. All have to be the same unit of pressure. Let's try that again. Then you can add them up. When I do that, I get 20.8 atmospheres. Okay, so next example here, example 2. It says a mixture of oxygen, carbon dioxide, nitrogen has a total pressure of 7.2 millimeters mercury. What is the partial pressure of oxygen if the partial pressure of carbon dioxide is 532 torr and the partial pressure of nitrogen is 0.12 atmosphere? Remember, partial means parts. So let's see what the parts are. Let's get our generic formula. We know the total is equal to oxygen. That's one gas that's described in the problem. Carbon dioxide, a second gas described in the problem. And nitrogen, the third gas described in the problem. Okay, so now we're going to add those, fill those in. So I did that here. I know that as I read this, I'm looking, so my question word, not my question mark, but my question word, I'm trying to find out what I'm solving for. I'm solving for partial pressure, or the pressure of just the oxygen piece. So that's here. So I have my total pressure, which I'm given here as I come across this number. As I keep reading, I see that this is the pressure of carbon dioxide, and this is described as being the pressure of nitrogen. So I plug those in. Now, I can't add these and subtract these. I would add these and subtract them over, right, to get PO2 by itself. But I can't do that until they're all of the same unit of pressure. So the first thing I did is I converted everything. In this problem, I decided to convert everything into millimeters of mercury. You can convert to whichever unit of pressure you desire, unless it's specified in the question. So I could have converted to atmospheres, everybody, or I could have converted all of them to torr, or all of them millimeters of mercury. I chose millimeters of mercury in this example. So I took 532 torr and I did my factor conversions. And I got 532 millimeters of mercury, and I did 0.12 ATM, and I converted in millimeters of mercury. Okay, so then we're going to go to the next piece here and show you that I'm substituting in my conversions. So we had changed this from 532 torr to 532 millimeters of mercury, and we had changed this from 0.12 atmospheres to 91.12 millimeters of mercury, so I substituted in. I added these two and subtract them over. In other words, I try to get PO2 by itself. So 737.2 minus 532 minus 91.2, and I get 114. Okay, so now we have example 3. It says nitrogen is collected over water. I made that pink for a reason at 50 degrees Celsius. The volume of the gas is collected is 1567.0 milliliters at a pressure of 6.52 atm. What is the pressure of the dry gas? So we know if we read through this, the only gases that are described are water vapor, because it's collected over water, and dry gas. So this is the Dalton's Law formula. It's shorter than the one we just used twice, but it's the same formula. I'm just being very specific. This is my P1 and my P2, or in this case, water and dry gas. If you go into this folder, Schoology folder for this video, you will see a link to a YouTube video where a gentleman, another chemistry teacher, demonstrates how we collect water over gas. Please go in and watch that video and come back to finish your notes. Welcome back. Okay, so now that you know what that looks like and got a visual for that, let's go through this a little bit further. So we know that P total is P water plus P gas. So I'm going to go and say that P total is equal to P water plus P gas, just using color schemes here. And it says nitrogen is collected over water at 50 degrees Celsius. Notice as I read through this, I have a volume. I don't have any place to plug in temperature or volume at this moment, because the only thing I'm dealing with is a change in pressure, or pressure totals. So I don't need my volume and I don't need my temperature as far as mathematically plugging into my algebraic formula. So I do have one pressure, and if you read through this, it describes the pressure of the dry gas. That's what we're solving for. Let me back up. We're solving for dry gas. It gives us the total pressure. How do I know this is total pressure and not dry gas? Because it tells me I'm solving for dry gas. So I'm going to put in my 6.58 atmospheres of pressure into my P total. And then I'm going to figure out my P gas. Now, where does this 12.3 kPa come from? Well, the pressure of water must come from the vapor pressure table. So I'm going to look at the temperature, because if you notice, the vapor pressure table comes in temperature and pressures in kPa. So I have all kinds of temperatures, and then they correspond to the right, slide to the right for the kPa. So I know that the water is collected at 50 degrees Celsius. So then it should be 50, I go to 50 degrees Celsius, I slide over, and I see it's 12.3 pressures. What kind of pressure? 12.3 kPa. So I plugged in 12.3 kPa in water, and then I'm going to solve it. Remember, I cannot do any math if I don't have like units of pressure. So I had to convert my ATM into kPa. I put it in its place. This is just a conversion factor. And then I subtracted 12.3 kPa from 668 kPa, and I get 656 kPa. If you are doing this problem, this may need to be adjusted to 6.59. So fix that before you start. And I should have mentioned that in the beginning, but I honestly forgot about it as I started going through. So from 2021 year, after 2021, I have changed this to 6.59 instead of 6.58. So this comes out to a more reasonable number. So just make that note. If you come out with 666 something here, then that's the old number. No big deal, whichever number you used. If you use 6.58 here, you're going to get 6666, but that should not be the case if it's after 2021. Okay, example 4. So now we're looking at example 4, and as I read this, it says a volume of gas, 139 milliliters at a pressure of 967 torr. If the pressure of the dry gas is 1.8 atm atmospheres, what is the pressure of the water vapor, and what is the approximate temperature of water the gas was collected over? So we have two questions here. What is the pressure of the water vapor? So we need a temperature to determine that, and we don't have that, so we're going to have to use our algebraic formula to do that. And then the second question is, what is the approximate temperature of that water when we get that pressure? So we're going to work that vapor pressure table backwards. So P total equals P water plus P gas. Only two gases in my container are water and gas, so water vapor and dry gas. So I'm going to bring these problems over. I'm going to read through this. It tells me that this is dry gas. I know I'm solving for water vapor, so then by default I know this is P total. So I'm going to put 967 torr equals P water plus 1.25 atm. I don't have like units, so I did a conversion. I just showed it down here. Okay, so that's where I get the 1.27 atm. Okay, and so then I'm going to subtract 1.27 and 1.25 to solve for P water. That's where I get P.03 atmospheres. And let me pause there because I do see a typo mistake here. Let me fix that. I'll be right back. Okay, I fixed that. It should have been 0.02 here. So then I took so this is my answer for P water in atmospheres, but now I need to figure out the temperature. In order to do that, I have to get it into kPa to use that vapor pressure table, which is down here. So our answer is fine to say, first answer is fine to say 0.02 atmospheres, but I need to have kPa to use the table, the vapor pressure table, because it's in pressures of kPa. So then I'm going to convert 0.02 to kPa. I got 2.03 kPa, and I see that it's between 1.5, well, I'm sorry, between 1.8 and 2.1, so somewhere between 16 and 18 degrees Celsius, so approximately 17 degrees Celsius. Okay, final example for Dalton's Law 1. It says determine the partial pressure of oxygen collected over water if the temperature is 301.16 Kelvin and the total gas pressure is 98.74 kPa. Okay, so we know P total equals P water plus P gas. P total equals P water plus P gas. Just a little bit of coloring there to help you understand. It says collected over water, so I know I'm going to use the vapor pressure table, right? Anytime it says collected over water, we're going to be using this vapor pressure table. I'm going to take and find out that I have this as my total as it's described. It tells me I can look up my P water by using the temperature. So this is the temperature in Kelvin, but our vapor pressure table is in Celsius. So I have to convert back to Celsius to use the table, which I did. 301.16 minus 273.16 is 28 degrees Celsius. So now I know the pressure of water at 301.16 Kelvin is 3.8 kilopascals. So I put that here, subtract the 2, and I get 94.94 kPa.